In this video, we are going to look at enzyme kinetics. That is how enzymes speed up the rate of a chemical reaction. Don't forget to like and subscribe after watching the video so you can receive every update from this channel. So basically, enzymes are proteins, molecules that serve as biological catalysts in a human system. In doing so, they speed up the rate of a chemical reaction by bringing down the activation energy of the reaction. So let's say we have a biochemical reaction where we have a substrate A being converted to B in a time period T. So this reaction here can take millions of hours before it can come to completion. But if we add an enzyme, the enzyme acts as a catalyst and speed up the rate of this chemical reaction. So let's say if this reaction will take, let's say, an hour before it can complete, when you add an enzyme, it can just take, let's say, 10 minutes or even less, so it can come to completion. This A, we call it the substrate of the enzyme, and it binds the active site of the enzyme here. Or the A is the reactant of this reaction. Normally, in every biochemical reaction, the concentration of the substrate or the reactant drops as the time increases, whereas that of the product increases as the time increases. So for every reaction, we consider for every biochemical reaction, if we have a curve of the concentration of the reactant A like this against time T, what is going to happen is if we have a higher concentration of the reactant, let's say here, as the time increase in this direction, the concentration of the reactant will keep dropping till it gets to where the enzyme is saturated or is completed. Inversely, the product concentration will increase. So let's say it has 0 to keep increasing in that manner. So this is a typical rate curve. The rate or the slope of this curve gives you what you call the rate of a reaction. So what is the rate of a reaction? So when we say the rate basically refers to the time period for the disappearance of the substrate or the reactant to form the B, or the time period for the appearance of the B from the A. So if you have, let's say, this substrate A being changed to B in a time period T, the time period for the disappearance of the A to form the B is what we term as the rate. And that period, basically, if you add an enzyme, that the rate of the reaction will increase. That is, it becomes very fast. So in a mathematical expression, we see the rate of a reaction from this curve is given by the concentration or the change in the concentration of A over the change in time. So this is a mathematical expression for the rate. It can also be expressed as a product, as also the same expression, the change in the concentration of the B over the change in time. Now, whenever we say a change, then a change basically refers to a differentiation. So this one can also be expressed as the differential of A over the differential derivative of T. So that's how we basically express the rate of a chemical reaction. Now look at something. As we said earlier, when we have the A being changed to B for every biochemical reaction, as the time increases, the rate or the concentration of the A will drop, whereas that of the B will increase. That means that if I want to find the change of the A, which is basically the final over minus the initial, it is going to give me a negative value. So whenever you want to express the rate in terms of the reactant, because it drops in concentration with time, we normally add negative sign in front. In the same way, if you want to express just the B, the change in the B becomes the final, which is a minus the initial, and that value gives you a negative or a positive quantity. So the rate in terms of the product is always positive. Let's have a typical reaction. Let's say you have hydrogen gas plus oxygen Of course, this reaction is going to give you a water molecule, which looks like this. Now, if you express this one as a rate, or if you express the rate of this reaction, let's balance this equation first. So we have 2 atoms of hydrogen here, then 2 atoms of hydrogen. You're gonna have 2 atoms of oxygen, you have just 1. So let's just put 2 here. Now when you put 2 here, then this one becomes 4. So you have to put 2 here too. So we balance this equation. The value 2 which is in front of them is called the coefficient, or the stoichiometric coefficient. And that depicts the moles of each of the molecules taking part of the reactant. So here we are blending hydrogen gas and oxygen to form the water. So if you want to measure the rate of this reaction, it is the time period for the disappearance of the hydrogen to form the water, the time period for the disappearance of the oxygen to form the water, or the time period for the appearance of the water molecules from the hydrogen and oxygen. I think my marker is a bit clear. Let me use the blue one and see. So if I have to express the rate of a reaction from this, then the rate can be expressed as, so the change, basically if a molecule has a coefficient, this value, we call it stoichiometric coefficient. Then you have to express this one as rate. You are going to take the reciprocal of that value. So you're going to have 1 change in hydrogen gas, so it's negative because it is a reactant, over the change in time. So here it's going to be over 2, so it's 1 over 2. So if you want to find the rate of a reaction with respect to a reactant or a molecule, and it has a stoichiometric coefficient, you're going to take the reciprocal of that value and multiply it by the rate. So this one can also be equal to the change in oxygen concentration over the change in time. This one can also be written as the change in water concentration over the change in time. So here it is product, so it remains what? Positive. So that's how we can express the rate of this reaction in terms of the individual participant in this biochemical reaction. Now let's look at the rate curve as we illustrated earlier. Now the rate curve is like this. That is a rate of a reaction. You can have a reactant. This concentration is measured in molar. They can have the time, basically measured in seconds. So as we said earlier, for every reaction, as the time proceeds, the concentration of the reactant will drop. So if you have the concentration, if here is 0, if here is 0, that is as time 0 and concentration 0, then the concentration is up initially at any point here. As the time proceeds in this direction, then you are going to have the concentration of the reactant also dropping at the same time, like that. So it drops because for the reactant, as the time progresses or the time proceeds. So for this curve, it is a plot of the concentration of the reactant against time. So the slope of this curve, which is basically the tangent that touches a line or say a point on any of the curve, is the rate. So if I want to find the slope of this curve, I will just draw a tangent to touch just one point on this line. So if I want to find the slope at the initial point here, where the time is almost 0, that's going to give me a rate, and that rate is what they call the initial rate of the reaction. So the initial rate of the reaction is basically the slope, that is all the rate found at the time which is almost 0 or the time 0. So at the starting of the reaction, the rate found at the beginning of the reaction where the time is almost 0 is called the initial rate. So as the name implies, it is initial rate because it is found at the initial of the reaction. Now, as the time progresses, if you pick a rate at any instant, if you find a rate at any instant, or let's say at any point in the curve, that is, select a particular point in a curve and find the rate at that particular instant. The rate there is found what is called the instantaneous rate. Instantaneous rate. So basically, initial rate too can also be said to be an instantaneous rate, but it is found at time zero. So the instantaneous rate is the rate found at any instant, and that is basically found by drawing a tangent to touch the line at just one point. Then you find the slope of that tangent. That's going to give you the rate. So that is the instantaneous rate. So let's also assume I find the rate at 2 points. So let's say I find the rate at 2 different points, this point and that point. If I find the rate at 2 different points and find the average, that is called an average rate. So the average rate of a reaction, we say it is the average of two rates on the reaction curve. So the rate here and the rate here. I said the rate here because the rate here refers to the slope of this point, and the rate here, if I draw a tangent here and find its slope, it is the rate at this point. If I draw a tangent here and find its slope, it is the rate at this point. When I find these two different rates and I change the average of that two different rates, that rate is called an average rate. An average rate. So the average rate, we say it is the rate that covers a particular time interval. So if I find it here, it means the time interval from here to this point is the rate I found. Even if I pick the point from here and here, the time interval from here and here is what I found. So if I get this rate here and I find this rate here, then I find the average. That is the average rate, and it's the rate that covers a particular time interval from this time, which is somewhere here, to this time, which is somewhere here. So that is the explanation of the rate curve. Now let's come to what we mean by the rate law of a reaction. Basically, the rate of a chemical reaction can be influenced by several factors. So how fast or slow a reaction can proceed can be influenced by several factors. So if I want to convert my substrate A to my product B, as shown earlier, several factors can influence how fast or slow this reaction can proceed. One, you can have the surface area where this reactant is, or the surface area of this reaction. We can have the temperature of this reaction. We can have the presence of catalyst. We can have the concentration of the reactant. We can even have pressure in the reaction medium. So all these factors affect the rate of a reaction. So for instance, if you have an increased temperature, that's going to increase the intramolecular condition, and that will proceed the conversion, or that will increase the conversion of A to B. So several theories are used to explain how these factors affect the rate of a reaction. For instance, how temperature affects the rate of a reaction is explained by a theory called the Arrhenius theory. Now, the concentration of a reaction of a reactant can affect the rate of a reaction in a theory which is known as the rate law. The rate law, whereas the presence of catalysts like an enzyme can be explained by the activation energy theory. So let's look at how the concentration of a reactant can affect the rate of a reaction. So normally, if you increase the concentration of a reaction or of a reactant, we expect the rate to also increase because the substance becomes so available for the enzyme to convert it to the product. So what is the rate law? Now the rate law says that the concentration of a reactant is proportional to the rate of the reaction. So the rate law says for every reaction, the rate of that reaction is proportional to the concentration of the reactant. That means that the reactant concentration can affect the rate of the reaction. If you increase the concentration of the reactant, then you expect the rate to also increase. So this proportionality sign can be converted by bringing a constant called the rate constant, K. with a number up here, which is, let's say, M. This K here is called the rate constant. The A is the concentration of the reactant. Then the M is what we call the reaction order. We are going to explain them one by one and see how each of them affect the rate of a reaction. So the concentration of the reactant A can affect the rate in several degrees. So the reaction order M here is the degree at which the reactant concentration affects the rate of the reaction. We can have it in a zeroth order, we can have it in the first order, in the second order, or the third order. Now this value can be determined through experiment. So we are going to find it in the next slide. We have what we call the rate constant K, which is basically affected only by the temperature of the containing medium or the reaction medium. So how the rate constant is affected by temperature is explained by the Arrhenius equation, which we are going to look at in the next video. So this is the rate equation that says that the rate of a reaction is affected by the concentration of the reactant, the rate constant, and the reaction order. So we are going to look at how each of these can affect the rate of a reaction. Bear in mind, we said the rate of a reaction is a ratio of the reactant concentration over time. So we can say that the unit of the rate is molar per second. Then we can have K, then the unit of the A is what? Molar, because it is concentration. M. So this means that the value here or the order of the reaction will determine how the unit of K will be. So this is just a brief explanation. Let's look at something. Let's look at the reaction order in details and how to derive the unit of the rate constant K. So when we say the reaction order as we saw earlier from R equals K into bracket A to power M. The value M here is what we call the reaction order. And the reaction order is the degree at which the individual reactant in a reaction affects the rate of a reaction. So let's say we have a biomolecular reaction where the two reactants A and B. It means each of these reactants affect the rate of reaction in different degrees. And the degree at which they affect the rate of the reaction is what we express by the reaction order. Now, if the rate of the reaction is not affected by the concentration of the reactant, then we say the reaction is in zeroth order. So let's say the rate of the reaction is not affected by the concentration of the reactant. Then we say that the reaction is in zeroth order. That means that if you change the concentration of the reactant as the reaction proceeds, there's going to be no change in what? The rate. If the rate of the reaction is proportional directly to the concentration of the reactant, that is to say, if the rate is changed by a factor that is used to change the concentration of the reactant, then we say it is inverse order. So let's say when you multiplied the rate by 2, the concentration also increased by what? Multiplication of 2. So when you increase the concentration of the reactant by a factor, the rate also changes by the same factor. In that way, we say what? The rate of the reaction is proportional directly to the concentration of the reactant. That's what we call the first order. Now, if the rate of the reaction is proportional to the square of the reactant concentration, which is this. So this one means that if you increase the concentration of the reactant by, let's say, a factor 2, the rate of the reactant will also increase by the same factor 2 to power what? 2, which is what? 4. That is what? Second order. So if the rate was, let's say here was 2, and the reaction is in second order, and you change the concentration of the reactant, let's say it was 5 here, you change this one by 2 to make what 10. If this reaction is in second order, since we changed here by 2, the rate will also change by what? The same power 2 to power 2, which is 2 squared 4. So the rate will eventually become what? 8. In the same way, if the rate of the reaction is proportional to the concentration of the reactant raised to power 3, that we say is what? In third order, and so on and so forth. So know that for every biochemical or chemical reaction, the rate of the reaction is affected by the concentration of the reactant, and the degree at which the rate of the reaction depends on the concentration of the reactant is shown by the reaction order. So the degree can be of the 0th order, the 1st order, the 2nd order, or the 3rd order. So having understood this order of the reaction, let's see how we can derive the unit of the K. As we said earlier, the unit of the K depends on the reaction order. So if you are being asked to express a typical first order reaction, so if you have two molecules, A and B, in the case shown above, where each of them affects the rate of the reaction differently, when they ask you for the overall order of the reaction, it is the sum of the individual orders of the reactant. So let's look at something. Let's see how we can find the unit of K for different reaction orders. So for every reaction, the R, which is the rate, is proportional to the concentration of the reactant A, where this A can change. So if it is a 0th order reaction, then of course you are going to have the rate of the reaction to be equal to K, because the K is what? Or the O, A to power O, the 0th order reaction is what? 1. For that matter, the K becomes what? M S to power 1. So for a 0th order reaction, the unit of K is molar per second. Now for a first order reaction, where the R equals K into bracket A to power 1, since this A is molar, the K can be expressed as molar, or let's say R over A. The unit of R is what? Molar per second over the A is what? Molar. So from this one will cancel this. So for a first order reaction, the rate constant has a unit of per second. Now let's look for a second order reaction, how it will look like. Now for a second order reaction, just from this, we are going to have the K to be equal to the R over A to power 2, because it's a second order reaction. Now this one is M X minus, so it becomes molar per second, which is for the rate, over the molar squared. So what will happen? We are going to have one of the M cancelling this M. So the final unit of a second order reaction for a rate constant is what? Per molar per second. So this is the unit of the rate constant for a second order reaction. Try this for a third order reaction. Let's see. So for a third order reaction, we must get molar 2 minus per second. For a fourth order reaction, let's get molar 3 minus per second. So try it and let's see. Try for a 10th order reaction and drop your answer at the comment section. So we said earlier that the rate of a reaction, the rate constant of a chemical reaction, and the reaction order can be derived from experiment and not from theory. So let's solve this question on how to find the rate constant and the reaction order. So we have two questions here. This is for cycle, this is question 1, and this is question 2. So we are going to do the question 1 together. When we are done, then I will leave the question 2 for you to try your hands on and drop your answer at the comment section. So take your calculator and let's do this together. After I'm going to leave the second question for you. So you try your hands on and drop your answer at the comment section. So let's try this one. So determine the reaction order for the reactant in the reaction below, given the table of data on the initial rate. Now you are to write the rate law for the reaction below and determine the value of the rate constant K. So our tasks are, we are to write the rate law for the reaction and determine the value of the rate constant. So the rate law relates to the rate of a reaction to the reactant concentration. So let's see how we can go about it. So let's begin by writing the rate law of this reaction. So for the I, the rate law of this reaction can be written. We have iodine chloride plus hydrogen gas equals iodine plus hydrochloric acid. So what we are going to focus on is the reactant, because the rate law relates the reactant concentration to the rate. So we're going to do nothing to the product. So the rate law of this reaction can be written as R equal to, now we have the K, which is the rate constant. Now we are going to write a hypothetical reaction order for each of these reactants. So we have the first one, which is iodine chloride. This one has an unknown reaction order, which is A. This is what we are going to look for. Then we have hydrogen gas, which is H2, with also an unknown reaction order, which is B. So this is the rate law, a hypothetical rate law for this reaction. Our task is to look for the reaction orders and also determine the rate constant. So let's first look at this. Let's try to explain this table. Now this table is a trial made on how this individual rate, how concentration of the iodine chloride and hydrogen gas affect the rate of a reaction. So we have experiment 1, 2, and 3. Think of it this way. We have a containing vessel that has 1 molar or 0.1 molar of the iodine chloride, then 0.1 molar of hydrogen gas. And for this, the rate of the reaction was 0.002. So think of it this way. So in the containing vessel, we have 0.1 concentration of iodine chloride, then 0.01 concentration of hydrogen. Then we have the rate of the reaction to be 0.002. Now in the second trial, what the experimenter did was that the experimenter maintained the concentration of the hydrogen gas to be 0.01 and changed the concentration of 0.1 of the iodine chloride to 0.2 in the second trial. So from the second trial, since there was no change in the hydrogen gas, any change in the rate is going to be attributed to that of the iodine chloride, because the hydrogen was maintained but the iodine chloride was changed. So here there was an observed change of the rate from 0.02 to 0.004. So this change can be said to have caused by what? The iodine chloride, because the iodine chloride is what we changed its concentration. Now in the next red experiment 3, what did we observe? We assume from the experiment 1, the experimenter maintains the amount of the iodine chloride, which is what, 0.1, then change the amount of the hydrogen from 0.01 to 0.04. So from experiment 1 to experiment 3, if we take this 2, this change in rates can be said to have caused by what? The concentration of the hydrogen, because the iodine chloride concentration was maintained to be 0.01, whilst that of the hydrogen was changed to 0.04. So let's see how from this experiment we are going to determine the rate order of the reaction and the rate constant. Now from here, we are then going to, I'm just going to leave the second one for you to try your hands on. We are going to determine the whole of this for the second table. So let's first start. We are going to take the experiment 1 and 2 and find the ratio of the rates. So for the experiment, we said the rate is equal to this. So let's make the hydrogen negligible. Let's just neglect the hydrogen and make use of the iodine chloride, because the iodine chloride is what was used. So the iodine chloride R, the rate was given by what? K into brackets iodine chloride L to power A. So we are going to look for the A. This is the rate expression for the iodine chloride alone. We are going to find the iodine chloride alone because the C or the hydrogen was maintained. So we are going to have experiment 2 over experiment 1. So how will it be? The rate of the experiment 2 is what? 0.0404 over the rate of the experiment 1 is 0.002. Now this is equal to, let's look at something. The concentration of the experiment 2 is what? 0.02. So we have 0.02. Now this one will raise to power A, because the order of the reaction of the iodine chloride, we assume it is what? 0.02. It's 0.02, so it's 0.2, sorry. So it's 0.2. So it is 0.2, so 0.2. Then the rate of the concentration of iodine chloride for the experiment 1 is 0.1. So you can pick 0.01 or 0.10 or 0.20, the same thing. Now each of these have rate constant in front of them. So the rate constant times each of this, of course, it will cancel out. Then each of this will be into brackets the order, which is what? A. So this is, you have A here, you have A here, and from indices when you have two values having the same exponent, it's just like you having the same exponent for all of them fractions. So this is how it's going to be. Now let's break this down. 0.04 divided by 0.0, take your calculator and punch. You must get 2. So the K will cancel the K. Then 0.2 over 0.1 will also give you what? Equal to 2 to power A. So here the exponent is what? A. So this A from indices, if you have 2 equals A, then it means that the power of this one, which is 1, is the value of A. So from here we can say straightforward that A is what? 1. Now from our equation, the A is the order of the iodine chloride. So it means the iodine chloride is in first order with respect to this reaction. Let's find the second one, which is that of the hydrogen gas. So the hydrogen gas rate can be expressed as the K into bracket hydrogen gas to power B, or the B we said added the exponent or the reaction order for the hydrogen. So for the B, since we have a maintained constant value of the iodine chloride for experiment 1 and 3, we are going to use experiment 1 and 3 for this calculation. So for the B, we are going to have experiment 3 over experiment 1. And for that, the experiment 3 rate is what? 0.008 over experiment 1 rate, which is 0.002. So what is this? Now the concentration of the hydrogen gas for experiment 3 is what? 0.04. So we have 0.04 over the concentration of the hydrogen gas for experiment 1 is 0.01. So 0.01. So all of them will have K in front of them. So when they have the K, they will eventually cancel out. So the order of the concentration of the hydrogen is what? B. And that's what we are looking for. So from this expression, let's look at something. We can say that 0.0, let's have point this one, 0.02 over 0.08 over 0.02 will give you what? 4. And that equals to what? 0.04 over 0.01, which is also what? 4. So we have 4B. So from this, we can equally see that what the rate of the reaction A, we can see the reaction order B is what? Also 1. So that here the B is also equal to what? 1. So that means that the hydrogen gas is also in first order with respect to this reaction. So the reaction orders are said here. The order of the iodine chloride is first order, then that of the hydrogen gas is also what? First order. So if you were to write this one using the values, we can get the rates. The rate expression can be written as R equals K into bracket the iodine chloride to power 1, which we can neglect because it's first order, times the hydrogen gas also to power 1. So this is the rate expression. That's the first part of the question. And the next part of the question says that you have to determine the value of the rate constant K. So from this expression, from this, I'm going to use the red one because the place is occupied. So from this, the K will be equal to the rate divided by the concentration of the iodine chloride to power 1 times the concentration of the hydrogen gas also to power 1. So when you get here, if you want to find the rate constant, having expressed this, then you choose any of the trials. So you can choose the first trial, the second trial, and the third trial, and you use the respective rate, the concentrations. So you have to use, if you want to take the first trial, use the rate of the first trial, then the individual concentrations of the two reactants in the first trial. You'll be wrong when you use this rate and use the concentrations in the second trial. So the K will be given as, let's use the first trial, 0.002 divided by the concentration of the iodine chloride is what? So the first trial is 0.1 times the concentration of the hydrogen gas is 0.01. So bear in mind, if these values you found here was in first, second order, then here we'll move raised to power what? 2. So this one becomes 0.1 to the power 2. So let's find the value. So we have 0.02, let's point to 0. So we have 0.1, then times 0.01. And that gives you 0.001. So we have 0.002 divided by 0.001. So the rate constant K is therefore found to be what? 2. Now use the same approach here and find the reaction order of this reaction, the rate expression or the rate law for this expression, then the rate constant for this table. Sometimes the question will ask you what will be for the rate of the reaction if any of the concentration of the reactant are changed from here to here. In that, just maintain the reactant orders and put the values in. So try this one and find or put the answer at the comment section. So let's continue with the integrated rate law. So the order of a reaction and the rate constant can be determined or predicted from a plot of the rate of a reaction against the time in integrated form. So the rate law of a reaction can be integrated, and how the curve of that integrated equation present can be used to predict the order of the reaction. Now let's build this fundamental. For every straight line, each equation can be expressed as y equals mx plus c. So this is the equation of every straight line. Now this y is the intercept on the y-axis. The m we say is the gradient of the slope of the line. The x is the coordinate on the x-axis. Then the c is the intercept. So if you want to present this, we can have a graph of the y against x. So with the graph of y against x, we can have the y here, then the x here. When you have a positive slope or the positive gradient, means that as the y quantity increases, the x also what increases. The slope, the c is the intercept on the y-axis. So if you want to just draw this curve, it will go in this direction, where the point this line cuts the y-axis is the c. So from this, as you increase the y quantities, the x quantity also will increase. If we have this expression y equals m minus mx plus c, that is to say, if the gradient is now negative, what does it mean? It means that as you increase one quantity, the other quantity will decrease. So this expression can be written or drawn as this, where here is y and here is x. So for this, if the gradient of the curve or the line is negative, it means that the line goes in this direction. That means that from here, this is the y value. From here, as you increase the x value, the y value was decreases. That's the meaning of you having a negative gradient. Now the rate of a reaction or the rate law can be integrated to form a linear, to have a linear equation where you can use to predict the rate or the rate constant and the order of the reaction. So the integrated rate law helps to determine the order of the reaction as well as the rate constant K. That is what the integrated rate law help us to determine. Now we will do a bit of integration here. So we have R, as we said earlier. If a reaction A proceeds to give you B, then of course the rate of the reaction we said earlier can be given as the dA, that is the D change in what? The concentration, change in the concentration of A over change in time. The rate can also be expressed as the rate equation can also be written in this form. So from this expression, the rate of the reaction can be written as this or that. So since we make reference to the reactant, then here must be what? Negative. So if we want to consider a zeroth order reaction, for a zeroth order reaction, this expression can be written as the A over the T equal to K. So this is for a zeroth order reaction where the concentration of A has nothing to do with the rate. So in this, the A is what? 1. So we can just ignore this. Now the integrated rate law helps us to integrate a particular rate law or rate expression to a linear form which is equal to y equals mx plus c, and that will help us to predict the rate constant and, if possible, the order of the reaction. So from this, we want to have the integrated form of this expression. Then you must determine the integral of both sides. So let's see how we can integrate both of these. So for us to integrate, let's first make this one linear. So we're going to have minus dA equals k dt. So the k here multiplies the dt. What I'm going to do next, let's move this negative here from this side of the equation to that side. So we are going to have, implies that we're going to have dA equals minus k times dt. Okay, let me make it a bit deeper. Minus k dt. So then we are going to find the integral of both sides. So we're going to integrate both sides of the equation. So we are going to find the integral of both sides. Now the integration is the change in the concentration of A from a particular concentration to what? A final concentration. So for this reactant, where A drops to form what? B, the initial amount of A is what? A naught. Then the final amount of A is the A at any time, AT. In the same way, the initial time here is what? T naught. Then T. Now let's see how we can integrate both sides. Now we pair the laws of integration. Integration is just the change in the concentration of something. So look at this. If we want to integrate a particular quantity and the initial amount is higher than the final amount, the integral of that quantity becomes just the quantity at the particular time, AT, minus the quantity at the particular time, 0. Now with this one, because the time drops or increases from 0, the initial is 0 and the final is what? A particular value. The integral quantity will just cancel out the differential quantity. So we get minus kt. So that's how the parameter will look like. So now let's look at this. Let's maintain the AT at the left side of the equation. So we can have the AT is equal to AO. So when it moves there, it becomes what? Positive minus KT. So this expression is the integral expression of every zeroth order reaction. That means for every zeroth order reaction, when we have a plot of the concentration of the reactant at any time t against the time itself, we are going to have a negative slope. and the intercept is going to be initial concentration of the reactant. So let's see how we can have a graph of this. So a graph of AT against time t will have a negative slope. So negative slope means that as you increase the time, the concentration of the A will drop. So the graph will look like this. So when it goes this way, this side, the point on the y-axis where the curve cuts is the A naught, which is the initial concentration of the A. Now the slope of this graph is what? Negative K. So for every zeroth order reaction, or when you see any graph where a plot of the concentration of the reactant at individual times against the time itself, and you have a negative slope or a graph of this nature, then this graph or that reaction is in a zeroth order reaction. Let's continue for a first order reaction. So for a first order reaction, you must get the A over the T to be equal to what? K into bracket A. So that's how it looks like for a first order reaction. Where here is 1, you can choose to ignore. Now let's see how we can integrate this one too. So for us to integrate, the first thing to do is, let's group like terms. Let's move this quantity of A to this side. Then take this dt to this side. So we're going to move cross multiply. So we're going to have minus dA over A. That's A concentration to be equal to K dt. Next, move the negative to this side. So we have minus K, and this side becomes what? Positive. The next thing to do is to integrate both sides of this expression. So we are going to find the integral of A from A naught to AT, then the integral of a time from T naught to T. Now bear in mind, for the principles or the laws of differentiation or integration, if you have the integral of the x over x, this one is the same as find the natural logarithm of the quantity x. So this is the law of what? Integration. So if you want to find integration of A, as the concentration dropped from A naught to AT, then the integration value becomes what? Ln of AT minus ln of what? Natural logarithm of A naught. And that one gives us what? As we said earlier, the integration will cancel differentiation, so you get minus KT. Let's maintain the ln of AT here at the side of the equation. So we have AT equals natural logarithm of A naught. Then we have minus what? KT. This expression can be attributed to that of what? A straight line, where you can have y equals mx plus c. So here is y, that is in AT, natural logarithm of AT, equals the intercept, which is in of A naught minus what? KT. So let's see how the graph of this one will look like. So if you plot a graph of natural logarithm of AT against t, you must get a negative slope, which will just look like this. Then the slope of that curve is what? K minus k. The intercept on the y-axis is in A naught. In A naught. That means that when you have a curve of in AT against t, then we have a negative curve or a negative slope. That curve or the reaction can be said to be for a first order reaction. So for every first order reaction, a plot of the natural logarithm of the various quantities of the A at different times against the time itself will give you a negative slope. Don't confuse yourself with the zeroth order. This is the first order. The zeroth order says that if you have a plot of the AT against time, it's gonna give you a negative slope. Then the first order says that if you have a plot of in AT against t, it's going to give you what? A negative slope. So this one is in AT and that one is what? AT. So this is for a first order reaction. Let's finalize this with a second order reaction. So for a second order reaction, we can say that the change in A, let's speed up, over the change in T can be equal to the K into bracket A to the power 2. So in grouping like terms, we can have minus D. Let's even move the minus the next step. So you can have dA over A squared is equal to minus K dt. If you find the integral of both sides from the law of integration, if you find the integration of dx over x squared from integration, this one is equal to minus 1 over x from the laws of integration. So let's look at how we can apply this one here. So if you want to find the integration of A or change in A from A naught to AT, where the A naught is more than the AT, that is, there's a reduction, then it's going to be expressed like this: the minus, which comes outside the bracket, 1 over AT minus 1 over A naught equal to KT minus KT. So let's push this minus into this bracket. We're going to have minus 1 over AT plus 1 over A naught, and that is equal to minus KT. From here, let's group like terms. Let's move the 1 over AT to one side of the equation, then the KT to the other side. So if you move the 1 over AT to this side and the KT to this side, we are going to have 1 over AT to be equal to 1 over A naught plus KT. So for a second order reaction, it means that when you plot a graph of 1 over the AT, that is 1 over the inverse of the various concentrations of the reactant at different times against time, you are going to have a positive slope. So with this, you're going to have a graph which will look like this. So it's a positive slope, means that as you increase the y quantity, that is 1 over AT, the x quantity too will increase. So it will go like this. The slope of this curve, the slope of this curve is what, k, then the intercept is 1 over a naught. So that's how basically we can derive the integrated rate law. So if you have a graph of 1 over 80 against t and you have a positive intercept, you can now conclude that what that graph or that reaction is what in a second order reaction. Let's see how we can solve sample examples. So the initial concentration of a reactant in first order is 0.05 molar and the rate constant of 0.02 molar per second. Now the first question A says what will be the concentration of the reactant after 10 seconds? Then B, how long will it take the concentration to reduce to 0.1 molar? So these are our try questions. You're going to apply the integrated rate law to solve them or to solve it. Now I have a multiple choice objective questions video on the channel already, so I'll put the link at the description section of this video so you can access it and just use it to test how much you understand today. So let's look at this. It said the initial concentration of the reactant in a first order is what? 0.1. So we know that for every first order reaction, the AT is equal to minus K plus A naught. That is the integrated rate law for a first order reaction. So for every first order reaction, when you plot a graph of the AT against time with the A naught as the intercept, you're going to get a negative slope. So let's deduce the parameters from this question. So the initial concentration of a reactant, the A naught, is what the question gives us what? 0.5 molar. And the rate constant, the K, is given as what? 0.02 molar per second. Then we have what will be the concentration of the reactant after 10 seconds. So we have the T to equal to 10 seconds. Then, so this one is A naught. Then we want AT. The first one, the AT is what we are looking for. Then the B, so the A, we want the AT. Then the B part of the question, we want what? How long? We want a time given the AT to be equal to 0.01 molar. So let's see how best we can solve this question. Let's look at the first one. So for the first one, the AT is unknown. This one is unknown. We know the K, we know the time, we know the A naught. So let's just put the value of the K, the T, and the A naught in here. So for the A, you can say the AT, which is the one we are looking for, is equal to minus KT. So minus KT. The K is 0.02. Then the time is 10. Then we have plus A naught, which is given as what? 0.5. So we are going to have the AT to be equal to, so we have 0.02 times 10, and that is 0.2, so 0.2. So minus 0.2, minus 0.2. then plus, we're going to have 0.5, so 0.5, and that gives us 0.3. That means that after 10 seconds we must get the concentration of 0.5 reduced to 0.3. So that is what molar. That is for the A. Then for the B, it says what will be, how long will it take the concentration of to reduce to what, 0. So this one is what, 80. So to find the time for the B, from this equation, the T can be made the subject as A T minus A naught over minus K. So you want a time. So let's put the values in there. The AT is the final concentration, which is given as what, 0.1. So we have 0.1. Then minus the A naught is the given initial concentration, which is 0.5. So 0.5. Then all over the minus K. The K given in the question is what? 0.02. So it's minus 0.02. So let's take it. We are going to have 0.1 minus 0.5, which is minus 0.4 over minus 0.02. So the minus and the minus will cancel out. So you're going to have 0.4 divided by 0.02, and that gives us what? 20. So it means the time required for the initial concentration of 0.5 to reduce to 0.1 is what? 20 seconds. So that's a solution to the sample proposed question. So check at the description section of this video. We're going to put a link to the previous MCQ we did on enzyme and chemical kinetics on what we've treated today. Thanks for watching. Don't forget to subscribe and prescribe the video to whom it may concern. Thank you.